Those who haven't seen one of these, this is an example of a, don't show this again. This is an example of a binary evolution channel, such as might be proposed to, for example, form a close binary neutron star pair that eventually merged due to the emission of gravitational waves. And a lot of these binary evolution channels, they start with a normal pair of stars with different masses. One undergoes stable mass transfer. Eventually, it gets stripped, it blows up, leaves behind a neutron star. There's an additional mass transfer phase as the secondary grows to giant proportions. And then there's a magic happens here box. And that winds up with the binary being dramatically shrunk in size, and then there might be additional mass transfer episodes, another supernova producing another pair of binary stars. But this magic happens here box is kind of it's kind of a missing link. We kind of know what starts, what needs to go in and what needs to come out, but the exact process by which this happens is still a little bit mysterious, and the question, a lot of questions about whether it can produce, for example, the necessary N spiral to produce the rest of the channel are still kind of uncertain. And of course, the missing link in evolution is exactly this sort of thing, and was first used to describe what was expected between apes and humans. But of course, we know now that humans are derived from an earlier species about 2 million years ago that didn't, we don't descend from apes, we descend from a common ancestor. And so, right, so stellar multiplicity. It turns out that most stars are in multiple systems. They may be binary systems, they may have additional pairs, additional members. And if we plot the multiplicity in the triple or higher order fractions as a function of primary mass, you see that for stars like the sun, it's maybe 50%. But as we climb up to massive stars above 10 solar masses, almost all of the stars are in multiple or binary systems. And a large fraction of those are actually not just binary systems, but they have two companions or more. And one of the kind of interesting, more or less recent examples of this is this sextuple eclipsing system where all of these binaries eclipse. And this was discovered by Tess a few years ago, this Tyche 703789-1. And this is just kind of one of the most extreme examples. But we can expect this to happen a lot, and especially if we're talking about massive stars. So one of the other things that we sort of have solid conclusions about for single star evolution is kind of a mature field, but the binary interactions are still a major uncertainty. Is that stars become giants after they finish hydrogen core burning, right? You can tweak various parameters, overshooting parameters, mixing length theory parameters. You can make them rotate, things like that. But none of this really changes the fact that they get big. And the other thing is that they leave behind compact remnants. Right? So, for example, if we look at the radius evolution of a 5 solar mass star and compare it with the with a companion that maybe is a 2.5 solar mass star, the orbital separations we would need. You see that on the main sequence, it grows somewhat in mass, but only by a factor of a few. And then when it starts climbing the red giant branch, it dramatically increases by an order of magnitude or more. Helium ignition starts at the tip of the red giant branch, which causes the star to collapse a little bit, to shrink as its core expands. And then it starts, when it reaches the end of core high helium burning and starts shell burning, it returns to the asymptotic giant branch and starts to expand again. So this is what we call, if there's an interaction between the stars in this phase, we call it case A. If it's in this phase where there's shell hydrogen burning, we call it case B. And then if it's after core helium ignition, we call it case C. This is just sort of the lingo that people use to describe these, binary interactions. As you can see, most of the interactions between stars are going to happen in the cases where there's the largest radius expansion. And up here we've got, this is, let's say, about 1 AU, so this sort of gives you an idea. This is the distance of the Earth from the sun. So these stars get quite large. If we look at the period or the separation distribution of binaries, we find that for low mass main sequence binaries, they have kind of a log normal distribution, which means that if you plot log A, it looks like a normal distribution in that quantity. For high mass main sequence binaries, it's more or less flat. This is Opic's law. And if you compare, let's see, so these are FGK, so like the Earth, like the Sun binaries. If you look at those binaries in metal core situations, more of them are close binaries. So the whole distribution is kind of shifted inward some. And notice that this is, here we've got 1 AU right here. So the fun ones, the ones that actually will interact, are a sizable fraction of the total. Right? At some point in their evolution, at least one of the stars is going to get at least this big, if not this big. Right? So if they started off with an orbital separation in this range, then at some point during their evolution, one of them is going to interact with the other, if not engulf the other. So what happens when you do that? Well, there are a few different ways to share mass between binary stars. One of the most common ones is called Røslov overflow. And the Røslov is it's a simplified representation of the potential due to the effective potential due to binary stars. So we treat the binary stars as each point masses, so M1 and M2, and they're separated by some distance A. But it turns out that the whole potential can be scaled by that separation. So we plot X over A and Y over A. And if you include not just the gravitational fields, but also imagine that they're orbiting in a circular orbit, this is what the effective potential looks like. We've got the inner Lagrange point, outer Lagrange points, and then two additional Lagrange points. And if you've followed things like where JWST lives and stuff like that, and if this were the Earth and this were the Sun, this is the place where those telescopes typically go, because it's very stable. You can orbit that point without much energy. And this is assuming that they're point masses. Of course, the real potential depends on the internal distribution of matter in these stars, but especially for giant stars, most of the mass is concentrated in the center. Like for a 1 solar mass star, an AGB star with a 0.6 solar mass carbon-oxygen core, most of the mass is actually in a space the size of the Earth. So these are actually a pretty good approximation. So what happens when a star grows? Well, it can, if it grows just a little bit, it stays within the range of influence of its own gravitational field, and the matter that it contains doesn't spill over into the other star. But if it fills its Røslov, then matter is going to start to fall onto the other star through the easiest channel it can take. And if you think about, say, a bathtub that's filling with water and it has kind of a little dip in one edge, the water is going to overflow in that spot first. And when it does so, this point actually, although it looks like it's the center of mass, it's not the center of mass. And so this material here, we're in the rotating frame, remember, this material here has angular momentum. And so when it falls over onto the other potential, the other Røslov, it's actually going to be deflected. And unless this companion is fairly large, it won't fall directly onto that star, but instead it'll create an accretion disk. Yeah.
Maybe this is like a dumb question, but the mass and the potential I would think are related. So like to overfill the potential, is there like a special condition that needs to happen there?
So like I said, this is a pretty good approximation to the overall potential. So yes, the internal distribution will change what the Røslov is doing, but if most of the mass is concentrated in the center, then this envelope is kind of this very low density stuff that will just expand and will not change the potential that much.
Yeah. So it's like the envelope that's extended beyond the physical size of the Røslov.
That's right. Yeah.
I see. Okay.
Yeah. So this is a region in space within which this star's gravity dominates, and it can hold on to everything. If stuff spills over here, it's going to go out. Yeah. So we can have situations like this where you have a stable accretion over here, as long as this star is less massive. Actually, the condition for stability is actually a little bit looser than that. But as long as this star is less massive than this star, it can all happen kind of on a thermal timescale. The timescale it takes for this star to respond to the loss of mass by readjusting its internal structure. And so you can have lots of systems like this, but sometimes you get a situation where because of the shrinkage of the Røslov, or the speed at which this is increasing, or the fact that this is a more massive star than this star, this has a convective envelope. If those conditions are holding, then the companion may fill its Røslov as well. It may be feeding it faster than it can take material in. And if it does that, well, you have now what's called the contact binary system. And under certain circumstances, these actually bizarrely can be stable, but under most circumstances, they're not. And so this can happen then. Then the material starts to leave the binary itself, and the easiest next place to go is through L2, right? So if you lose matter through L2, then the binary develops a kind of a spiral of material taking away mass and angular momentum from the whole system, and as a result, the two spiral together. Right? So what happens when that occurs? There's supposed to be sound here. There we go. Yeah, so exciting stuff happens. And here's an example of a suspected post-common envelope binary. Common envelopes are the case where the two spiral together, and now the two cores of the stars are actually embedded within the same envelope. Well, so this is a particular system. I think it's about, actually not sure what the distance is, but about 800 years or so ago, it's thought that this underwent a situation like this. It's a binary now with a few day period. And this is an ALMA observation with the blue stuff sort of moving toward us and the red stuff moving away from us. And a 3D reconstruction has this as being sort of an equatorial concentration and an equatorial disk with a more or less along the line of sight outflow, fast moving outflow, 150 kilometers per second moving both away and toward us. And this is what it looks like in the optical. I like diffraction spikes because they're punchy, you know, they're really, you know, some people hate them, but I love them.
Paul, how long is the common envelope phase and what sets the time scale?
I'll talk about that. Yeah, good question. Yeah.
When you said boom, is that like an event of some sort then?
Yes, also. Okay. Oh, thank you for asking these excellent questions. Yeah, so here's an example where the binary doesn't seem to have survived. Right, so this is an actual merger. So some of us call this a failed common envelope, but you know, others just call it a merger. So this is an B1309 SCO. This is I think the total mass is constrained to be maybe a few solar masses, but this was observed by Ogle, which was, of course, was originally scanning a part of the sky looking for microlensing events. But under, you know, basically looked like a normal nova at one point, but quickly revealed itself to be strange. It started to get redder, which novae don't typically do, and it lasted quite a long time here. It didn't decay in the same way that a nova does. And so Salenda et al. Went back and looked through the Ogle archives and so realized that this star had been observed regularly for a long period of time. And they were able to identify first a two-peak periodic structure that became one peak shortly before the eruption. And they were able to get a period. And look at this nice in-spiral of this orbital period, right? It's orbital separation as well. This is starting from something that's pretty close already. This is 1.4 days. And this is only 1.42 down here, but it's you know, declining right up until the time that the eruption occurred. So they consider different things. You know, could this be spots? Could this be a normal single star eruption? Things like that. And the best conclusion was that this is a merger. And so the expectation is that mergers will, well, this is one of our best examples, but there is a class of objects now known as variously as, yeah.
Is this a model or is just a fit to the data point?
This, good question. I mean, I don't remember whether this is.
Is there any model?
I think this, is there a model? Oh, yes. Well, sure. I mean, you could say, well, do a Keplerian orbit and then put a drag force and then say, you could do that sort of thing. I'm not sure. I don't remember what they did. Yeah. I mean, with the binary pulsar, for example, you use gravitational radiation to take energy up.
Yeah.
Right, so this is an example of a class of events known as variously as luminous red novae or intermediate luminosity optical transients or UV optical transients. And these things, the characteristic timescales, to answer your question, Brian, this characteristic timescales are maybe tens of days for these things. And the peak luminosities, here are classical novae and core collapse supernovae. They're kind of intermediate between the two. So we have yet another reason to overload the term nova, right, with things that are completely physically disconnected, right? So we have classical novae, which are eruptions because of thermonuclear explosions on the surfaces of white dwarfs. We have core collapse supernovae, where it's coming from gravitational energy release. Point 1A explosions, which are partial destructions of white dwarfs through thermonuclear explosions, and things like that. But now we have something else completely that's got the name nova. Yeah.
Why do you have a separate class for just calcium-rich transients? Like, why is that so important that it's labeled?
I don't remember for these, but some of these transients, like some of these things show sodium in their spectrum, which indicates that there was there's a circumstellar medium. There's some nucleosynthesis products that have been dredged up and then brought out. I don't know if that's the same for calcium. You know? Okay, so I don't know, but it might be something related, that sort of thing. So the existence of sodium lines in some of these type 1A spectra is taken as evidence that they might be from a what's called a single degenerate channel. So we expect to see more of these with observatories like Rubin, and as long as they look in the galaxy. Although some of these, as you can see, some of these are actually outside our galaxy. In fact, MAD5, that's in the Virgo cluster. So these are bright enough to be seen, you know, throughout the local universe, not just the local group. And there are a few in M31 as well. Right, so what kind of phenomena require stars to get this close? I mean, you know, we've got mergers which, you know, their closeness effectively goes to zero, but there are also a lot of situations where we need stars to be close enough and compact enough that at one point during their evolution, they would have been inside an envelope of the size in AU or so. And so those include X-ray binaries, for example, where the companion is a neutron star or a black hole, and depending on the mass of the donor star, you know, it's called a low mass or high mass X-ray binary, and some of them produce jets, you know, microquasars, novae, which are white dwarfs accreting from a companion. They build up a layer of hydrogen on their surfaces. It becomes degenerate. It blows up unstably, produces a thermonuclear explosion that brightens the system, but does not destroy this. Type 1A supernovae, which could be, you know, merging white dwarfs. You can get mergers of white dwarfs that don't destroy the pair of white dwarfs. You can get situations where something like this goes to the point where the companion star is close to the Chandrasekhar mass and blows up, and also situations where it's not close to the Chandrasekhar mass and blows up. Extremely low mass white dwarfs. These are helium white dwarfs that might be 0.1 solar masses. They would be, normally they'd be the remnants of low mass stars, but those stars, as people who are in 404 know, last how long in the main sequence? Order of magnitude.
10,000 years, 100,000 years.
Super long.
Super long, yeah, trillions of years.
Oh, I just love
So it's fair to say you're wrong. It's fair to say also that none of these have ever been formed through normal single star evolutionary channels during the history of the universe. Right, so, and yet they exist. How? Well, you can have one of these be the donor to something smaller, right? So more massive object, this massive object could be a neutron star, for example, losing mass. And this was maybe to start off as a normal, more massive star, more massive white dwarf that shrank, basically, shrank to become less massive white dwarf. Gravitational wave events, neutron star mergers, neutron star black hole, all of those. You know, in order for those to get close enough that gravitational radiation can cause them to inspiral the rest of the way within the age of the universe, you need some other thing to get them really close. There are a few different ways to do that. Common envelopes are one way. And then planetary nebulae. Well, I mean, we normally teach that planetary nebulae are the inevitable outcome of low mass star evolution. As the AGB phase ends, and the outer envelope is ejected. The core of the star zips across the HR diagram, and as it's turning the corner, it illuminates some of the material that came out, causing it to fluoresce, making the planetary nebula. But a large fraction of these look pinched like this, and a large fraction of them also turn out to have binaries in their centers. So it's starting to be argued that maybe all planetary nebulae are a result of binary interaction. And a star like the sun may not actually necessarily produce a planetary nebula as it's turning the corner there in the HR diagram. So which kind of goes against what you were taught in Astro 310. I told you not to show me that again. Computers just don't listen. Right, so common envelope evolution was originally proposed, actually, there's some possibility that Jerry Oestreicher or even our own Ron Webbe may have suggested this idea a few years before, but it wasn't until Bogdan Paczynski actually put pen to paper and actually published a paper that describes this. So he usually gets the credit. Although when I gave a talk on common envelope at Princeton, Jerry was in the front row, and his first question, well, no, his first comment, let's say, because his first question was about, so this isn't even Thorne-Zytkow optics are off the table, but his first comment was just to remind me of this fact. So common envelope, as I said, the two cores, because the mass transfer becomes unstable, they orbit within a common envelope, and then the big question mark is, under certain circumstances, they may survive as a much closer binary with an ejected envelope, with the energy needed to eject the envelope coming mostly from the orbital energy of the binary, or also alternatively, if quote unquote failed common envelope where they actually merge, and you have a fast rotating star like an FK Comet, right, Red Giant, for example.
Well,
Yeah.
are there other ways to have a failed common envelope phase? I mean, these are stars that are very evolved, are there stellar winds that are disrupting things?
Absolutely, yeah. In fact, and certainly Roche-Lobe overflow is not the only way that they transfer mass. So you get wind Roche-Lobe overflow. Although winds by themselves tend to widen binaries.
So is there a fraction of systems we expect to actually be able to enter and survive the common envelope phase, and is that consistent with the rates and things like that?
Well, part of the problem is that knowing which ones will survive is, I mean, we have the things like the energy formalism, which you're probably aware of, and I won't actually go into that unless people ask, but there are ways to predict this based on the internal structure of the stars, but they are extremely ad hoc and don't take account of the complex dynamics that go on here. So I'm not sure how much to rely on. Yeah.
So given the physical constraints to develop a common envelope, are there some like spectral types that are preferred for this kind of?
Yeah, so the ones that will start to transfer mass unstably like this will typically be ones with convective envelopes. Because when you strip off a layer of mass from the surface of a convective star, its responses to expand. Because it'll typically have a higher entropy material underlying low entropy material. So it's like taking the cap off of something that wants to be bigger. If these are radiative envelopes, then more likely it'll be stable mass transfer. These are all just really general observations, not necessarily true in every specific case. Also, the systems that will undergo a merger like this tend to be ones with high mass ratios. So if I get in a spaceship and I go hop into the sun, right, I'm not going to cause the sun to eject its envelope. Right? So the mass ratio there is quite large. If I throw a planet in, if I throw Jupiter into the sun, also, that's like a mass ratio of 100 or so. So those systems will most likely merge. The systems that will most likely survive like this are ones where this is a non-trivial fraction. The companion is a non-trivial fraction of the mass of the donor. Yeah.
I'm curious if we have any observed systems that could be candidates for a common envelope, like that middle picture right there, or maybe.
Oh, in the act.
Like, do we have any possible candidates, or is this just like peer theory?
Well, so probably the best examples would be the things like B1309 SCO, which would have been caught in the middle of this during the peak of its brightness. So these luminous red novae, you could argue that there may be this kind of case, but the timescales for these are really short, and so this is why large angle surveys are so important. It's right time domain surveys, because you don't know where these are going to happen necessarily. I'll get into the explicit timescales in a moment here. Right, so this is an example of a simulation. This sort of shows you what happens when a common envelope is developed and how the two cores inspiral. So there's this long, slow phase to begin with, and then all the fun stuff happens really quickly on a dynamical time scale. And then what happens to the envelope is that it's ejected in more or less equatorially concentrated way. So this matches very well the HD 101584 case, where we have this equatorial slow-moving density concentration. And in some cases, it looks like these may actually also, during the process of common envelope, produce fast polar outflows like jets.
Paul, how much of the mass is ejected?
Well, in this particular case, not a large amount, and it's partly because we chose a system with a large mass ratio, and so we weren't able to resolve the full in-spiral. So this was still in-spiraling by the time if the separation reached the smallest separation we could resolve. So only about 10% or so, actually I'll show the number, but about 10% or so of the envelope was ejected. And it's thought, well, actually this is a good opportunity for me to talk about timescales. I'll actually get to that. Yeah.
What should the colors represent?
The colors this is just a rendering of density. This is a volume rendering, and I chose a transfer function that sort of emphasized the original surface of the donor star, and then but also allowed for the very low density stuff that was flying out to be resolved or to be seen. And so I wouldn't take it as meaning anything physical. So I gave you two outcomes, but yes.
You commented that there could be jet formation from this.
Yeah.
What is the jet launching mechanism?
That's a great question. I mean, so Fabian Schneider's group at HITS has seen this in MHD simulations. Actually, if we run this simulation beyond the point at which we feel secure in resolving the orbital separation, it does that too. There's no magnetic fields in this though, so it's just an interesting observation.
Some hydrodynamic.
Yeah, yeah. Right, so yeah, those two outcomes are not the only possible outcomes. We could have in-spiral mass ejection. It could stop at some finite radius or separation that we don't know yet. Well, then that material that's ejected, that may not go to infinity. It may hang around as a very thick disk. And so you can have what's called a circumbinary disk that interacts with the binary that's left over, maybe widening the orbit again, maybe causing it to shrink. Who knows? Depending on a bunch of things. And if it shrinks it further, then we might get, a delayed merger. If we have the original in-spiral, it could also lead to a merger. If we have a finite separation, the stars will continue evolving on their nuclear timescales, might get another mass transfer phase, and maybe that takes us back to the beginning again. Maybe it just does stable mass transfer. So there are a lot of different, you can imagine that one binary evolution channel I showed you that went to double neutron star, there are many branches. You have to think of these almost like branching ratios in particle physics experiments or something like that. And so there are people who do what's called binary population synthesis, who try to predict the population of things like that by applying very fast, simple models to these very short-lived phases, as well as doing sort of normal population synthesis of the single star evolution. And the results are very sensitive to what we assume about this and what we assume about which systems will undergo these different outcomes. So what we're trying to find out here, when do common envelopes happen? We have some handle on that. What occurs during a common envelope event, like what physics is important, which systems survive them, the ones that survive, what are their final separations, and then finally, what do they look like? And we think that, broadly speaking, they look like these luminous red novae. They get brighter, they get dimmer. As they get dimmer, they get redder. They have a lot of dust. They form a lot of dust. So we expect those things, but more detailed predictions are needed. So mostly what we're working on are these things right now. And what we're trying to do, and I'll say who we are in a moment, but what we're trying to do is to get to the point where we can predict this sort of thing as well. And this turns out, unfortunately, to be more difficult than it is for, say, supernova explosions, where you can make simplifying assumptions in the codes that do the radiation transport and produce the light curves. This stuff is all moving around like this. It's not moving homologously, and so some of those codes don't seem to apply. Right. So the timescales. So here's an example This is actually a low mass system from some time ago, but it shows the various phases. So we've got this actually a very long period of stable mass transfer that eventually becomes unstable, maybe because of L2 mass loss, maybe because of what's known as the Darwin instability. And then finally, that mass transfer becomes unstable and there's a dynamical timescale plunge. And that plunge is followed by an orbit of greatly decreased orbital separation that's initially elliptical, but its eccentricity is declining over time. And this period of time can be extremely long because it's driven by not dynamical timescale stuff, but thermal timescale stuff, the response of whatever mass is left inside the orbit to the change in conditions that it's undergone. And so, for example, if we can throw some numbers in, we consider a 10 solar mass red supergiant with a normal neutron star, an initial period, let's say 1,000 days, and a final period of 5 hours. So this tells you what kind of shrinkage we're talking about. We need to get down to maybe hours or even minutes of separation in order to produce all of these, this zoo of interesting stuff. And this loss of stability requires many, many orbits. They take thousands of years. And the dynamical plunge in happens really fast, maybe years, maybe months, maybe days. And then the slow spiral in this later phase is driven by basically dissipation of energy and further ejection in the envelope. But this orbit is nearly circular now, and so it's shrinking very, very, very slowly. So if you have something that's a code that can follow it on a dynamical timescale, that means you have to follow for many, many, many orbits, which is very inaccurate and very expensive. So if you just put some numbers in, you might say that this would require maybe billions or more time steps in order to follow the whole thing with a three-dimensional explicit hydrodynamics code. So these are the phases, like this and maybe 100 orbits after this are the kinds of thing that we can do in 3D. The other things have to be done in one dimension or something else, yeah.
So what stops the plunge in is just clears out too much material to lose any more energy?
That's a great question also. Don't know for sure. One possibility is that, so you spin up the core, and so there's less, the tidal effects are less, right? Another possibility is since you've cleared out a lot of mass, you're now experiencing less hydrodynamical drag. So there are a few different possibilities. So in the one-dimensional calculations that people sometimes do, one is that they do this energy formalism I alluded to. Another is that they may follow the end spiral until the conditions are right for the remaining material within the orbital separation no longer to overflow its Roche load. And so there are a bunch of possible stopping conditions, but which ones actually operate and under what circumstances is not known.
Oh, this is a naive question. So in these simulations, is there any impact? Is the dynamics have any impact on the nuclear reaction of the star?
Well, most of the time, no, right? Although the end spiral may actually go into nuclear burning regions, and then interesting things can happen, right? So if you, in fact, Natasha Ivanova did her PhD thesis on this. Under certain circumstances, you can have like a fresh inflow of hydrogen into a very hot region that's not burning hydrogen. Like it's hot helium, right? Hot ash. But you bring in fresh fuel was originally cold being a relative term, and then suddenly, but it's raised to this temperature. So so that can remove a lot of envelopes.
So that's including the energy equation of the.
No, not usually, no, because most of the time that doesn't happen. For most values of this efficiency parameter, the end spiral stops at a point outside of the nuclear burning region, outside of the shells. Right. Although for some of our calculations, we're getting close to that, and we're certainly getting to places where the abundances have changed because of previous evolution. Right, so right now, at least, what you have to do with this is to solve a problem with different codes. So for example, you use a stellar evolution code like MESA to solve the evolution of the donor star and the companion in 1D, and you can do this as a binary, basically having a model for stable mass transfer, and you let it go up until the point where the code predicts that there would be unstable mass transfer. And then you take the stars out. They're one-dimensional profiles, but of course, in reality, they would be distorted because of the Roche-Loeb overflow. So what we do for us is we actually we have an old custom-built SPH code, smooth particle hydrodynamics. We start them far apart, follow them in the co-rotating frame, and just push them together slowly until the donor adopts the characteristic shape. So this gets them closer to what they would actually be as they're about to enter a common envelope. And then we take this and interpolate it into an adaptive mesh refinement 3D code. The idea then is that somehow we put this back into Meso or some similar code to follow the long-term evolution. It's a little problematic though, because it's not really one-dimensional. You have a binary in there, and it's depositing energy in a way that's not spherically symmetric. So there have been attempts to do this. I think Vincent Bronner in particular, not Bronner, I'm not blanking on his name. Anyway, a student at Pitts also has looked at this. And there have been efforts to do this sort of thing just completely in 1D, sort of ignoring some of the details of what's going on here. That, as you've seen, this is an intrinsically, the dynamical phase is intrinsically three-dimensional, right? So you can't really do that in 1D.
How expensive is this?
So this is not too much. We can do this on our little cluster, but this is on the order of maybe 10 to 100,000 core hours, let's say something like that. So I think the biggest issue with, because we can use AMR to pretty aggressively just refine around the cores and then have a very large low resolution box to capture the ejecta. But the time steps get really short. They get like a minute. And if you're following something for years at a minute at a time, that's a lot of time steps. So unfortunately, that doesn't scale extremely well.
Sorry for the technical question. Is there a way to map this into some kind of effective one-body formulation that makes it more efficient? Or because I think here you're still very far away from any kind of merger. You probably look at a Newtonian or post-Newtonian framework.
That's right. Yeah. Well, these are all non-relativistic. So yeah, we certainly could do that. And so one idea I've had this summer, but haven't had a chance to sort of follow up on yet, is that maybe one could map this not into one dimension, but onto multiple expansion, and then to follow, use a spectral code to follow it. So this is something I just don't at the moment have time to work on. Idea for a project. Right, so the length scales also are kind of extreme, especially for AGV and red supergiant stars. We might need a factor of thousands, and even that's just to be able to say we have a zone spacing the size of the core, whether the core is a white dwarf essentially or whatever. But so what typically people do is for these cases is to replace the core with a particle that interacts only gravitationally with the gas, and to remove the appropriate amount of matter from the gas phase as well. So we follow the cores sort of as particles. There are various ways to do that. So the time scales and the length scales are big issues to manage. All right, so I have a couple of projects to describe with students, and probably won't get to this one, but so with Xiaojie, we're working on the effective evolutionary stage on the in-spiral and low mass giants, and in particular trying to produce cases for later study with planetary nebula ejection. With Camille Landry, who is a student of Andre Pecha's at Charles University, and she's now a postdoc at KU Leuven. We worked on a project that's about to be published on the effect that previous mass transfer phases have on massive giants. And then I've been working for a while on putting radiation hydro into these problems, because some of these systems have thermal timescales in their envelopes that are comparable to the dynamical timescales, and so you cannot neglect transport processes. This turns out to significantly modify everything, and of course, it's one step toward trying to predict accurate light curves. So part of the problem with these simulations is that they tend to stall at a point where they're not actually reproducing the kind of systems that we want to produce. And for a while, it's been speculated that maybe there's an additional source of energy to eject the envelope in addition to orbital potential energy. And the most natural example would be not nuclear, but recombination energy, because a large fraction of the envelope may be in a phase of partial ionization or full ionization. And when it gets expanded by the interaction, it cools and then recombines. Right? So you get 13.6 eV out of every hydrogen that does that. And so this has started to be included. So the original common envelope simulations were using gamma law equations of state, or in our case, Helmholtz equations of state that is assume full ionization. But more and more people are using things like the Mesa equation of state that include ionization state tables. And so, for example, Mike Cloud did a simulation of a 12 solar mass red supergiant and a 3 solar mass black hole using SPH, and tracked the evolution of ionization state. So typically what is found is that the hydrogen recombines maybe after it's already been unbound, so it's actually not helping that much, or it may do so under conditions that are optically thin. So the radiation that it produces, because every recombination produces a recombination photon, or one or more, simply escapes. Right? So it doesn't actually help in terms of ejecting the envelope. But the helium tends to recombine later, and it does so under higher density, higher opacity conditions, and so it's a greater chance of actually being useful. But so far, all of these simulations that have included this in the equation of state, none of them have actually done the radiation transport. So we actually, we just have bracketing of how much mass can be ejected. We turn off recombination, include recombination, see how much mass is ejected. You can get sort of a range of values, but you don't know actually which is the right one. So what Xiaojia has done is she's taken a single star, which starts off with 2.5 solar masses, and we've got a very low mass white dwarf of 2.36, and follow it at different evolutionary stages. Tip of the red giant branch, the early AGV, and the end of the first thermal pulse on the TP AGV. And this is the helium burning luminosity. So this would be a case B, and both of these would be case C mass transfers. And the radius, as you can see, after the tip of the red giant branch, there can be no common envelope during this part, because if there were, then we would have done it here, right? So the next available phase is when, on the early AGV, we again reach that radius. So these two stars have roughly the same radius, but very different core masses. In the case of the tip of the red giant branch, it's about 0.4 solar masses, and it's all helium. In the case of the early AGV, it's about 0.5 solar masses, and it's all carbon oxygen. As you can see, that changes somewhat the, not a whole lot, but the fraction of the total internal energy that's recombination energy. And the big one that I'm really interested in, Xiaojia, is the TP-AGV case, where we dramatically change that. This one turns out to be really tough because the resolution requirements are so much bigger. This may be a factor of 10 bigger in radius. Actually, the 10? Yeah, 10. Right, so this is what it looks like. This is just the low resolution case, right, with the big box. Yeah, so you can see that we can capture most of the ejecting material for for the dynamical phase at least. Eventually, the stuff will escape the box, and we'll have to keep track of it some other way. But don't see huge differences here between the two cases. In the case of the edge on, so that was face on onto the orbit. Edge on, we see some differences here. The red giant seems to be expanding in a more equatorially concentrated way than the early AGV. And if we compare the orbital in spiral, so this is an earlier small box high resolution run that we did that unfortunately some material started to leave the volume, so our estimate of the mass loss was kind of had problems with it. So we decided to start doing large boxes, and so far we've completed low resolution versions of that, so we're not able to follow it as far. But we see now we're able to follow all the unbound stellar material, and for the early AGV phase, it seems to be significantly larger than the RGV. Although still, let's see, this is 0.4 solar masses, so this is a sizable fraction of the envelope. Do you remember what the core of the star, that's right, 0.5 solar masses. Yeah, so that leaves, from 2.5, that leaves 2 in the envelope to start with. So it's a sizable fraction. The azimuthal averages, so one of the things we want to do is produce azimuthal average densities, and you can see with the RGB that it's still, this is at the first perihelion after the initial plunge. You see that it's more equatorially concentrated. What we expect is that when we feed this to a collaborator who does 2D simulations of planetary nebulae, that when he puts a fast wind here representing the planetary nebula, the fast wind that generates that, it's going to produce different results. And we've done this already with some of our earlier simulations and found that we can reproduce a lot of these bipolar structures just because this equatorially concentrated material, this movement is dense, it's moving slowly, but this low density, high velocity, fast wind gets blocked basically in the equatorial plane and is free to move in the polar directions. So we can definitely produce things that look like these bipolar planetary nebulae. And the reason he can do these, he can follow these for a long time, is that he's got a two-dimensional grid for one thing, and it expands with time. He also has all the non-LTE stuff in it. Right, we can produce other things as well. And it's sort of like, here's a thing, we make something that looks like it. Here's another thing, we make something that looks like it. We've included magnetic fields, and those can produce these highly collimated flows. And there are other instabilities that can develop at late times that also match some of these cases. This is an example of a study that Ursula DeMarco led with one of the first observations from JWST of the Southern Ring Nebula, trying to reproduce its features. And I think that it actually came up with a scenario in which there were 5 stars originally. So it was kind of a complex scenario, but this is an example of Guia Garcia Segura's simulations trying to reproduce the radiation hydrodynamic instabilities that you see in that nebula. So just to summarize our sort of initial results, the later stage with the larger core produces a less equatorially concentrated ejected material. And then it also combines more mass and faster. And that we expect when we put it in these planetary nebula things will be important. Okay, so I'll just talk about the CE with rejuvenated donors. So here's another one of these binary evolution channels, and this shows some of the branches that can occur. So this one is for type 1a supernovae, and both single and double degenerate progenitors of type 1a supernovae. And you can get situations where things don't succeed in going all that way, or they wind up as a merger, but you may get more than one or more common envelope phases that are not the first mass transfer phase. What does this mean? This means that if you were evolving these 2 stars as separate single stars, right, and then you put them into a common envelope simulation, that you should have considered the fact that the now donor was once an accretor, for example, or in this case was a donor that lost some of its material and evolved further before it underwent this event. So the structure is not going to be the structure of a single star. What's more, it may be rotating faster than it would have normally been because it would have created angular momentum as well. Yeah.
So, I mean, naively, I'd expect the more these common envelope phases to have, the closer your mass ratio is going to get to unity or something like that. Is that actually what's seen in your simulations?
So we're doing individual cases, not looking at population statistics. So I think that's what would be needed to answer that question. Yeah, and
yeah, I mean, one of the headaches with double degenerate systems is why are they all standardizable?
Yeah. Yeah, well, that seems like something we could ask people who do binary population statistics. Okay. Right. So if it's the second or third event, that means the structure of the donor is different than it would have been as a single star. So Mattia Renzo and Ylva Gutberg looked at what happens to a star after it's been the accretor in an initial mass transfer episode, and they looked in particular at a model for Zeta Oyuki, which is a single star now, but maybe a runaway from a binary in an earlier phase, and was the accretor at some point. So they allow it to, I forget what they start with, 25 solar masses initially, and they allow it to evolve until it would have evolved along this track, right? This is the accretor. I guess this is a 17 solar mass one. It would have evolved along this track as a single star, but it was interrupted by accreting mass from the companion that caused it to swell up and get hot, and then gradually to cool, and then evolve back to this point. And the idea here is that at this point, the donor, which is more massive, and its fate is sealed. Even though it lost mass, its core is now on an evolutionary track where it's going to burn everything and going to blow up. So it blows up, and then they follow the remaining accretor as a single star and see what it does. And you see that it seems to kind of follow the single star track with the additional mass added, but not exactly. And so its internal structure winds up being different. It turns out to have an internal structure that is, especially in the core envelope boundary region, has some steps in it. So these are models with different, these are, I think, polytrope models anyway, with different amounts of rotation. So just consider the red and the orange here. This is a single star model. It's got this normal ramp up in entropy, owing to the shrinkage of the burning region on the main sequence. But this rejuvenated accretor has higher entropy in this region and has some weird steps that I don't completely understand. Anyway, so the idea is that the rejuvenated accretor has a lower binding energy in the envelope. So if you look at, for example, the orange case here, this is negative binding energy, let's say. So going up is more bound, going down is less bound. You see the rejuvenated binary has an envelope that is lower binding energy and therefore might be easier to remove. So that's the idea. Does that really work in practice? So we did simulations with this. Because this was done as part of the Kavli summer program in astrophysics at the Max Planck Institute for Astrophysics, we were trying to construct a project that could be where you could make a lot of progress in 6 weeks. And so one of the things we did, since we didn't have equation of state tables for this metallicity, we just used a fully ionized equation of state. But what we did was we compared two stars that were both about 18 solar masses, one of which had been rejuvenated, and one of which had been evolved as a single star. As you can see, their internal hydrogen abundance profiles were very different. It's non-rejuvenated. It's got the normal single star evolution track profile, and then the rejuvenated one has these weird steps. I think these were both about the same radius, about 500 solar radii, so pretty large stars. So, so we look at the non-rejuvenated cases as looking down on it, this is looking from the side, and sort of blanket with the rejuvenated case. You see there are some differences. These are somewhat different phases of evolution, but you see there are some differences in the equatorial concentration. They both developed this kind of same structure where there's essentially we carefully looked at this. There's a pressure supported circumbinary disk here. Material here is still being ejected. It's more than pressure supported, and then material out here is just moving more or less ballistically. One thing that we found was that the rejuvenated cases spiraled in much faster. They went from the same initial condition, essentially, in terms of separation, down to where we almost couldn't resolve it further in spiral. So these are consistent with merger cases. We don't know yet whether these could be real progenitors of binary neutron star systems. One problem was that this is an 18 solar mass star with a 1.4 solar mass star. So the mass ratio is pretty large, and they very well could merge instead of surviving as a binary. What we should have done was a binary black hole progenitor. But anyway, so we may do that yet. So we had to follow this only until we ran out of resolution. So you can see there are some differences. This is about the point, you see a weird difference here. This is occurring just as the companion is going from the Roche-Loeb overflow separation down to the surface of the companion. And I should say also that these, again, it was in the interest of time, we didn't relax these donors with the SPH code, but we interpolated them directly from MESA. So there, it started off a little bit out of equilibrium. The unbound mass, we did not unbind a great deal of mass, certainly not as much as we did in the low mass cases with recombination energy. In this case, it's less than 10%, but we did find significant differences. So here are the rejuvenated, and this is including, let's see, so this is including no thermal energy in deciding whether a zone is unbound or not, and this is including it. So the reality is somewhere in between here, because it depends on how much thermal energy can actually be used to do work on the envelope. And so you can see there's maybe a 30 or 40% difference in the amount of unbound mass here. We need to follow it further in order to find out how much more we can unbound.
Okay, but I think that's still a large amount of mass.
Yeah.
And that is a lot of metals, presumably, as well.
Yeah, yeah.
How does the rejuvenated case then follow the more or less normal standard evolution track?
Oh, because these in the Renzo and Goodfried, this was not doing common envelope here. This is just saying, okay, the companion star blows up and goes away, or the primary blows up and goes away. How does the companion?
Yeah, so if you expect metal contamination, then it shouldn't.
Yeah, so it could behave very differently. Right, and so I think, let's see, did I? All right, good. Yeah, and so we also generated azimuthal over density plots, or azimuthally average density plots. Xiaojie did this, and we can see that there is a significant difference between these. So the rejuvenated case is also more equatorially concentrated. So these stars will not undergo planetary nebula phase; they're too massive. But if you follow this for long enough, and different things can happen that can illuminate material that's been injected a long time before. You might be able to learn something about the previous history of a system that does that. Anyway, so one of the main conclusions from this was that people doing this sort of work should not be using single stars to do their initial conditions. They should be considering end-to-end the whole situation, a given binary evolution channel. The rejuvenated systems inspiral faster, but eject less mass, so we can see, and produce more equatorially concentrated outflows. And then you should do the whole story. All right, so it's been an hour, so I will skip the interesting thing, except to say that for the very massive low metallicity binary black hole systems, what we've learned so far suggests that they don't work, at least from the common envelope channel. Right, so why is the creature elusive? It's extreme, but it's rare and exciting, but not a drama queen. It's intermediate luminosity. What do we know about it? Tides and shocks, these spiral shocks that get generated, do most of the work of actually transferring energy to the envelope and ejecting it. For the low mass systems, especially, the recombination energy is very important. And they're just beginning efforts to try to predict the light curves and color evolution. But our expectation is, given the temperatures of the gas and so on, that these will produce the same kinds of things that we see in the LRN, in particular red, slow, equatorially concentrated ejecta, and in particular dust. And so that's yet another thing that needs to be put into these simulations that people are just starting to do, like with something called the Bowen approximation. We need to make progress in different ways. You could have an observer, we're giving this talk, they'd say something different here, but as a theorist, I get to make rules. And so, we need this end-to-end treatment of evolutionary channels to consider the effects of previous mass transfer on the donor. We need to, especially for this long self-regulated phase, need to include radiative and convective transport. And I'd say radiative, especially for these very massive red supergiants that have these short thermal timescales. It's really essential in those cases. And then finally, we're just getting to this point where we can start predicting the light curves and spectra, but that would be needed too. Thanks. Yes.
Thank you for the really awesome talk. One thing I wanted to ask about the final point you made, since you showed some pictures of observations that might look like the systems that you're modeling, what kind of constraints would you be able to place on these computational studies from observations?
Yeah, interesting question. Well, so what would specifically would we want to learn from predicted light curves? We want to compare things like the rate of increase, and there have been some, like Andre Pekka has done some work with L2 mass. I think I might actually have that as a slide. He did simulations where they actually just tried to fix what was inside the L2 point and just follow the outflow around it, and in particular to try to reproduce B1309 SCO. And I had an example of the light curve be generated from it, but it did kind of very crudely match the rate of increase before the peak. Anyway, so that would tell you something about, especially about the outer envelope of the donor star and what its structure was. And then the rate of decrease of brightness at the end would tell you about how fast the material has been ejected, how fast it cools off and becomes optically thin eventually, how much dust was produced. So a lot of quantitative things about the initial system that we would learn from that. The smoking gun, right, for deciding what's the final separation, which is one of the main things we want to learn, is the actual observation of the remnant binary. And it's possible, for example, to use observations of double white dwarfs at known separations to then work backwards in a statistical fashion to figure out what their initial separations were. And that's one of the lines of argument that leads us to consider things like recombination energy.
Brian?
Oh, Brian?
Yeah, thanks, Paul, for the talk. So I was wondering about the composition of when you inject the envelope, about the composition. So it's in my contract. I have to ask about it. So at least in some cases, it's going to be full of fresh nucleosynthesis goodness. And is that something you can observe?
It should be able to be observed. Yes, absolutely. Yeah. So we expect the products of dredge up, right? So nitrogen enriched, and then in AGB donors we expect S process results as well. I don't know if we haven't been able to predict the spectra yet to do that comparison, but my expectation is that you'd be able to see that.
Cool. Thanks.
So Paul, I have a question. So most of the massive stars, like OB stars, they are in binary multiple systems. So this is a common envelope stage seems to be quite common.
Yeah.
So then our theory, or at least the theory that I'm familiar with, I'm teaching tomorrow. Thank you for just ruining my time. About this stellar evolution, single kind of massive star evolution passes are all messed up.
Yeah, I'd say so. Well, so it's definitely turning out that a lot of especially massive star evolution cannot be done just as single stars. That you have to consider, even if it's not common envelope, it's mass transfer of some kind. Yeah, and then of course there are lots of systems for which there were multiple systems, and you had things like Kozai-Ledoff oscillations or whatever, and so you had interactions. And so one of my favorite stars, which I think I've already shown in 404, Zeta Carinae, right, which we think might have its great eruption in the late 19th century, which was the century before I got my PhD. The great eruption may have been the result of a stellar merger, and then it started off as a triple. So two of the components merged, and then we see it as a binary now, but originally it was a triple. So those sorts of things happen regularly in the lives of 80 solar mass stars, and you have to account for that.
Okay, so we just ignore that part of the actual algorithm.
I guess so. Yeah, except that's the really cool part. Well, hot part.
Any other questions?
So not completely facetious. I know you have your reservations about AI, but if the issue is time resolution and number of time steps, primarily as the computational thing, is there a role for emulators or something that let you do large timescale predictions, things like transformer models?
Well,
Yeah.
I mean, I would feel, certainly for things like population synthesis, but I would feel better about because right now, I mean, that would not basically improve the level of metaphysical certainty over the models that are currently being used. What I would like to see would be some kind of, so what we're trying to figure out is when we do these different calculations, what's the right way to hand off the results of one to the next? Because to some extent, like when we're setting up the common envelope, the dynamical phase, the initial conditions that we're setting up are already dynamically unstable. So if you relax them too long, they're gonna do stuff, right? So you don't want that. But so what you'd like to do would be to extend that initial condition into the stable mass transfer phase some way. But that's expensive. Right? So how do you map from one stage to the next in a way that preserves the behavior that's appropriate? And especially then going to this later phase, which unfortunately, makes like we can predict what the final separation is. And then when I give a talk, the observers are always asking me, so what's the final separation? I'm saying, you don't believe that, what's alpha? What's this efficiency parameter? I'm sorry, I'm not going to tell you because I can calculate it, but it's meaningless, right? This 1,000 years afterward might determine everything. So if we could somehow do that, and I'm not saying do the whole thing in 3D, but do the whole thing in a quasi-rigorous way, then we could train AI models on that and then use them in these population synthesis codes.
Yeah, and the observations we actually have lots of, probably not going to ever be luminous red nova, but like Wolf-Rayet stars and things like that. There's lots of spectra there.
Yeah, that's true.
All right, let's thank Paul again.